In this video, we are going to look at linearization of functions. The reason we care about this is that nonlinear functions can be difficult to analyze directly. Straight lines are much easier to work with, so if we only care about behavior near one chosen point, we can often use a straight line to approximate the nonlinear function locally. This local straight line approximation is called linearization. Let's start with a straight line. One way to write a straight line is as y equals y naught plus m times x minus x naught. This form says that the line passes through the point x naught y naught. Here, m is the slope of the line. The term x minus x naught tells us how far and in which direction x has moved from x naught. So the equation says the y value at x is the y value at x naught plus the slope times the change from x naught. Linearization uses the same idea. The difference is that the straight line we use will be the tangent line to the nonlinear function. Now we take the straight line idea and apply it to a nonlinear function. Suppose we have a nonlinear function f of x and we choose a point x naught. At x naught, the function value is f of x naught and the slope of the curve is the derivative of f of x naught. The tangent line passes through the point x naught, f of x naught, and uses that slope. Near x naught, the tangent line stays close to the nonlinear curve. So we can use the tangent line as a local approximation. F of x approximately equals f of x naught plus the derivative of f of x naught times x minus x naught. In other words, we start at f of x naught, then use the slope f dash x naught to estimate the function value as x moves a small amount away from x naught. The important word is local. This approximation is meant for values of x near x naught, not for the whole curve. Now let's write the tangent line approximation in a form that will be useful later. Remember, we started from the equation of a line y equals y naught plus m times x minus x naught. For the tangent line at x naught, the value y naught becomes f of x naught, and the slope m becomes the derivative of f of x naught, f dash of x naught. That gives us f of x approximately equals f of x naught plus f dash of x naught times x minus x naught. Now we introduce one new quantity. Delta x equals x minus x naught. Here x naught is fixed. It is the point we have chosen to linearize around. The new quantity delta x tells us how far and in which direction x has moved from x naught. So delta x equals 0 means x equals x naught. It does not necessarily mean x equals 0. This is important. X tells us where we are on the x-axis, while delta x tells us how far we are from x naught. Equivalently, x equals x naught plus delta x. That means we can write the approximation as f of x naught plus delta x approximately equals f of x naught plus f dash of x naught times delta x. This says that if we move a small amount away from x naught, we can estimate the function value by starting at f of x naught and following the tangent line. To finish, let's step back and summarize what linearization means. The approximation we derived was f of x naught plus delta x approximately equals f of x naught plus f dash of x naught times delta x. This is a local approximation near x naught. That means it is not trying to describe the whole nonlinear function. It is only trying to describe the function close to the point we chose. The approximation is best when delta x is small. In Taylor series language, this is the first order Taylor approximation. A full Taylor expansion would include higher order terms, such as terms involving delta x squared and delta x cubed. In the linear approximation, we ignore those higher order terms, leaving the tangent line approximation. The same idea can be applied to nonlinear ODEs near equilibrium, where we approximate the behavior of the system close to an equilibrium point.